Good morning. Our lecture for this morning would be alternative pathways of carbohydrate metabolism. Objectives for the lecture are the following. Enumerate the different alternative pathways of carbohydrate metabolism. Illustrate the different steps of the pentose phosphate pathway. Enumerate the different steps of the uronic acid pathway. Illustrate the different steps of the biosynthesis of mannose, hexosamine, and sialic acid. Illustrate the different steps of glycogenesis. Illustrate the different steps of the metabolism of glucose. Correlate hemolysis with the clinical condition of glucose 6-phosphate dehydrogenase deficiency. So pentose phosphate pathway is an alternative route for the metabolism of glucose. So this occurs in the cytosol and does not produce ATP. There are two or irreversible oxidative reactions, and the reaction of the pathway produces 2 NADPH and 1 carbon dioxide. This produces ribose, and a deficiency in the pentose phosphate pathway would result in acute hemolysis of RBC or your G6PD. The first two reactions are your oxidative reactions, which are irreversible. It starts with your glucose 6-phosphate undergoing oxidative reaction to form 6-phosphogluconate using your glucose 6-phosphate dehydrogenase. This produces your first molecule of NADPH. And then your second reaction would be your 6-phosphogluconate, which would produce your ribulose F5-phosphate with your enzyme 6-phosphogluconate dehydrogenase, which produces your second NADPH. This would then be recycled and used in your reductive anabolic pathways. Then it would be followed by your non-oxidative reactions, which are all reversible. Your ribose 5-phosphate would be transformed into dehydrogenase 7-phosphate. Then your erythrose 4-phosphate. Then your cellulose phosphate. Then your cellulose 5-phosphate would turn into your glyceraldehyde 3-phosphate. Then your fructose 6-phosphate. And your glyceraldehyde 3-phosphate. Your last products would be familiar because they are products as well of your glycolytic pathway. Why is NADPH important? This is used because of your reductive biosynthesis and reduction of your hydrogen peroxide, so reducing your antioxidants. This is the biochemical basis of the use of glutathione. Administering glutathione would further remove these antioxidants and increase your NADPH in the process. So it aids in your cytochrome P40 monooxygenase system. So in your mitochondrial, it acts on your steroid hormones, bile acid synthesis, turns cholecalciferol to 25-hydrocholecalciferol, that is vitamin D3 to its active form. In the microsome, it detoxifies foreign compounds, activates or inactivates a drug or make a toxic compound more soluble. It's also involved in phagocytosis by the white blood cells and synthesis of nitric oxide. So a G6PD deficiency impairs the ability of an erythrocyte to form NADPH, resulting in hemolysis. This would result in oxidant stress, which would be triggered by certain drugs, infections, and fava beans. Our next alternative pathway is the uronic acid pathway. This catalyzes conversion of glucose to glucuronic acid, ascorbic acid, and pentoses. Uronic acid pathway does not produce ATP. So your uronic acid pathway starts with your alpha-D-glucose 6-phosphate, which is catalyzed by your phosphoglucomutase. It then becomes your glucose 1-phosphate. Then it would become your uridine diphosphate glucose to your UDP glucose pyrophosphorylase. Then it would become your uridine diphosphate glucuronate, then your D-glucuronate, L-gluconate, 3-keto-L-gluconate, L-cellulose, xylitol, L-ascorbate, and your L-dehydroascorbate. So what is important to note here that your ascorbate, your L-ascorbate cannot be synthesized in primates. So this is blocked in primate and guinea pigs. Hence, your primates do not have the ability to manufacture vitamin C. Then we have your fructose metabolism. So this is mainly from diet, and sucrose yields 1 fructose and 1 glucose. This is not insulin dependent, and this bypasses your phosphofructokinase 1, and your deficiency would lead to essential fructosuria and hereditary fructose intolerance. Your fructose metabolism, studied along with your glycolysis, is a secondary pathway because unless your intracellular concentration of fructose becomes unusually high, hexokinase is saturated with and phosphorylates glucose rather than fructose. So your hexokinase has a preferential treatment to your fructose 6-phosphate in your glycolysis. However, if there is oversaturation, only then would it activate your fructose metabolism. So your fructose 1-phosphate in your fructose metabolism would have its corresponding fructose 1,6-bisphosphate in your glycolysis. And your aldolase could act on your aldolase A, B, and C, could act on your fructose 1,6-bisphosphate, while only aldolase B could activate your fructose 1-phosphate. This would eventually produce your glyceraldehyde in your fructose metabolism and eventually produce your dihydroxyacetone phosphate. Deficiencies in your fructose metabolism enzymes will lead to essential fructosuria or hereditary fructose intolerance. Lacking fructokinase would lead to essential fructosuria, which is autosomal recessive and is a benign condition. Fructose accumulates in the urine, while hereditary fructose intolerance would be also autosomal recessive, but the absence of aldolase B leads to intracellular trapping of fructose 1-phosphate. This would cause severe hypoglycemia, vomiting, jaundice, hemorrhage, hepatomegaly, renal dysfunction, hyperuricemia, and lactocythemia. Fructose, sucrose, and sorbitol can cause hepatic failure and death. Treatment would be rapid detection and removal of fructose and sucrose from the diet. Another alternative metabolism pathway of carbohydrates would be your galactose metabolism. This would be your lactose, glycoproteins, glycolipids, and is not insulin dependent. Deficiencies in galactokinase, galactose 1-phosphate uridyltransferase could lead to deficiencies in galactose metabolism. So a galactokinase deficiency is a rare autosomal recessive disorder. This causes elevation of galactose in your blood, galactosemia, and your urine, which is galactosuria. It causes galactitol accumulation if galactose is present in the diet. Elevated galactitol can cause cataracts, and treatment is restriction of diet. Classic galactosemia is a deficiency of galactose 1-phosphate uridyltransferase or your GALT deficiency. It is an autosomal recessive disorder and causes galactosemia and galactosuria accompanied by vomiting, diarrhea, and jaundice. Accumulation of galactose 1-phosphate and galactitol in nerve, lens, liver, and kidney tissue causes liver damage, severe mental retardation, and cataracts. Prenatal diagnosis is possible by chorionic villus sampling. Newborn screening is available. Therapy would be rapid diagnosis and removal of galactose and lactose from the diet. Despite adequate treatment, at risk for developmental delays and in females, premature ovarian failure. A deficiency in aldose reductase is an enzyme present in liver, kidney, retina, lens, nerve tissue, seminal vesicles, and ovaries. It is physiologically unimportant in galactose metabolism unless galactose levels are high. Elevated galactitol can cause cataracts. Another alternative pathway, although nice to know already, would be your Mannose metabolism. So side by side with your glycogen and your glycolysis, your mannose would produce your alternative pathways from your mannose 6-phosphate, mannose 1-phosphate, and then it would produce your fructose 6-phosphate, which would be a precursor or a substrate for your glycolysis. So that is the importance of your mannose metabolism as far as alternative pathways are concerned. It could produce your mannose and your anchors, but remember that your mannose 6-phosphate could produce your fructose 6-phosphate and glycolysis. Same way with your GLC 6-phosphate would lead to your fructose 6-phosphate. Same way with your hexosamine metabolism, your glycolysis would have your fructose 1,6 diphosphate and your glucose 6-phosphate would have your fructose 6-phosphate. So your hexosamine pathway would provide your alternative pathways, bringing back your glucosamine 6-phosphate, your N-acetylglucosamine 6-phosphate with reversible products, bringing it back to your fructose phosphate and your UDP and acetylglucosamine and your UDP and acetylgalactosamine. And this would be a separate lecture. I understand in the following afternoon your glycogenesis and your glycogenolysis. If you would see your glucose and your glucose 6-phosphate and your G1P would be recycled and form reversible reaction such that it could go both ways. Okay? Same way with your sialic acid metabolism. So it would be through your glycolysis and your UDP. Then your sialic acid will bring back your um, Golgi and glycans and produce your sialo co-conjugates, and therefore um, feed on your feedback inhibition of your GNP. Then fucose, remember your mannose 6-phosphate would have your fructose 6-phosphate and would be transformed to your 40 to 6-deoxymannose and eventually be transformed into fucose. So the last three would just be nice to know. Please focus on your pentose phosphate pathway, your uronic pathway, your fructose and your galactose metabolism for your upcoming exams. Thank you.